All right, so if I can make this move, here's the problem we're going to tackle first. It's a lumped capacitance problem, right? We'll prove that here in a second. We have some kind of a sphere. It's got a radius of 1 millimeter. Here are the properties. It's exposed by convection to fluid at 25 degrees Celsius. Initially, the sphere is in equilibrium with the fluid, so T initial is T infinity. And then at time equals 0, you get this volumetric generation that's a function of time. So the volumetric generation goes from nothing to a time equals 0. It immediately spikes up to this guy here, G dot triple prime max, and then it decays exponentially back down to 0. And the time constant of that decay is 2 seconds. So this is what my volumetric generation looks like, right? It's sitting here at 0, nothing's happening, and then at time equals 0, this spikes up to this large value and then drops back down to 0 exponentially, and the time constant is 2 for that exponential decay, right? Okay, so that's our problem. Before we solve the problem, we got to do a couple things, right? First, we probably should verify that a lumped capacitance model is actually appropriate. So that's just a matter of calculating the Beal number. The Beal number says, I'd really like to ignore the resistance to conduction inside of this object and only consider the resistance to convection from the object to the surroundings. We're going to ignore convection or radiation here, so this is only convection. So the resistance to conduction is right here. It's my conduction length. Divided by my cross-sectional area in K, and then the resistance to convection is 1 over h bar times a sub s. So my conduction length I'm going to take as the volume divided by the surface area. We said that was one way to do that. My conduction cross-sectional area we said we take as the surface area, so that's where I put that. And this surface area and this surface area cancels out. So here's my Beal number, and it's 0.04, which is really pretty small. So I'm justified in making the lumped capacitance approximation. The other thing that's worth calculating before we start down the path of solving is the time constant, right? So the lumped capacitance time constant, the external time constant, is the total capacitance of this object times R convection. So it's the mass times the specific heat capacity multiplied by 1 over h bar a sub s, and it's 1.5 seconds. The internal time constant is something that we've chosen to ignore when we made the lumped capacitance approximation, right? The internal time constant we've decided is extremely fast. In fact, it must be about 4% of this external time constant. So the only time constant we care about is this external time constant. So it's worth thinking about what the reaction of this object must be given this time constant right here. So this is an interesting time constant because the size of the time constant, 1.5 seconds, in this length of the process, 2 seconds, are about the same, right? So you're going to get some interesting dynamics. This is the eventual solution that we'll get. But what you can see is, you dump this energy into the object, and the time required to put the energy into the object is about the same as the time required for the object to get rid of the energy. So you're going to get this kind of interesting response, and everything's going to be over after a few time constants. So here at 8 time constants, you're getting to sort of done. If you had a different situation where you calculated this time constant and you found it was really small, and again, nothing is ever small by itself, right? Here it's really small relative to the length of this process, then you could anticipate that what's going to happen is the object is going to basically, after some very short, 0.3, 0.4 second startup, is basically going to follow right along with what the volumetric generation is doing. And so you almost have kind of a quasi-steady situation where this object is always at a temperature associated with this particular volumetric generation. So if that's the situation, you might decide you don't really need to solve the problem because it's you basically know what it's going to do without solving it. The other possibility would be if you calculated this time constant and you found that it was large. So here it's 15 seconds, which is quite a bit larger than the time associated with the process. What's the object going to do then? Well, in that case, you actually have sort of two very different processes that are separated in time. You have an initial process associated with dumping all this energy into the object. That takes about 2 seconds, and then it's done. So you basically have a pulse of energy that gets put in the object. And then you have another process that takes, on the order of 15 seconds associated with getting the object losing that energy back out to the surroundings, right? So here you get this very large, fast temperature rise associated with putting the energy into the object, and that's a 2-second sort of process. And then you get a much slower decay back to T infinity, and that's a 15-second sort of process, right? So again, without solving anything, if you can understand things like resistances and time constants, you can get a pretty firm understanding of what's going to happen before you spend a lot of time trying to come up with a solution. All right, so let's try to solve this problem using Laplace transforms. The first thing we have to do is derive the problem itself, right? You're always sort of on the hook to do that. So my energy balance, because it's a lumped capacitance problem, my control volume can go around the entire object. I have Q dot convection crossing this surface. Inside the object I have some storage, and then I also have an input of thermal energy generation, right, G dot. So in is G dot, out is Q dot convection, and stored is du dt, right? So G dot is this volumetric generation, this function of time right here. That's in watts per meter cubed, and my energy balance has to be in watts, right? So I got to multiply that by the volume. Q dot convection is given by Newton's law of cooling. I drew the arrows going from the object to the surroundings, so this is T minus T infinity. And then du dt is the total heat capacity of the object, right? This is all the material that's inside of my control volume times d temperature d time. So with those substitutions, I get this differential equation. I'll divide through by rho times v times c, and it becomes this differential equation right here. So hopefully deriving that's pretty simple at this point in the class. My initial condition is that the temperature at time equals 0 is T infinity. So solving this with Laplace transforms is a 3-step process, right? We said that step 1 is take this problem and transform it to the S domain, and then solve it in the S domain, and then take the solution and inverse Laplace transform it back to the time domain. So let's do the first step, which is usually a relatively easy step, and that is take this problem and do the Laplace transform on the whole thing, right? So the first property we're going to make use of is this one right here, which says that there's 1, 2, 3, 4 terms here, but I can do them one term at a time. I can take the Laplace transform of this guy and add it to this guy, and that's going to equal this guy and this guy, right? So that makes life a little easier. So let's take the Laplace transform of the first term, which is what I've done here. So the Laplace transform of the time derivative is just S times T hat minus the temperature at time equals 0, which for this problem is T infinity. So that's what I'm going to substitute there. Then we're going to take the Laplace transform of this guy. So this is the Laplace transform of temperature, which is a function of time, multiplied by a constant. So this is where I'm going to use this property right here, which says that it's just going to be that same constant times T hat. So that's what I did here. Then I take the Laplace transform of this guy. Well, that guy is just a constant, right? T infinity is constant, tau is constant. So if I take the Laplace transform of the constant, it's just that constant over S. So that's what I have here. And then finally, I have to take the Laplace transform of this guy here. So this is a constant times an exponential. So it's going to be that same constant multiplied by the Laplace transform of an exponential. So if I go over here, the Laplace transform of an exponential is 1 over C plus S minus C. So for here, My c is minus 1 over a, so this is going to be 1 over s plus 1 over a. And that's that. So I make these substitutions, 1, 2, 3, 4 of them, and I get this problem right here in the S domain. And sort of as promised, my problem in the S domain is quite a bit simpler than my problem was in the time domain, right? There's no derivatives in the S domain for this lumped capacitance problem. It's just algebraic and t hat, right? So I just have to do some algebra, right? I'm solving for t hat, so here is a t hat term, and here's the other t hat term. So if I collect them, I get t hat times s plus 1 over tau. I'll bring this minus t infinity to the other side. And then I just divide through the whole thing by s plus 1 over tau. There's my solution in the S domain, right? So the last step then is to bring that solution from the S domain back to the time domain. And this one isn't so hard. For sure Maple could do this for me. If I look at this, this last term is really simple. That's going to be an exponential, right? These other two terms are a little harder. So this is where using the method of partial fractions could be really handy. I can take this term right here, for example, and I should be able to break it up into a term related to 1 over s and a term related to 1 over s plus 1 over tau, right? So I have two distinct factors here. So that's what I did over here. I clear the denominator, which means multiply by tau times s plus 1 over tau. So that gives me t infinity, and then a c1 times this stuff, and a c2 times this stuff. And then I just equate like terms. So my constant term is t infinity has to equal c1, and then my s to the first power term is 0 has to equal c1 times tau plus c2 times tau. This has to, there's an S missing here, I'm sorry. There's an S right here. So C2 times tau. Right there. All right. And so this is pretty easy to solve then. This says C1 is minus C2, and C1 is T infinity. So this term here becomes this right here. And of course, the whole point of this is that that's easy to inverse Laplace transform. That's just a constant. This is easy to inverse Laplace transform. That's just going to be an exponential. Okay, so I have one more term here that I have to do the same thing for. We'll do that one a little bit more quickly. You can sort of look at it and make sure you understand it, but it's the same idea, right? This is made up of distinct factors, so I have a term related to each of those distinct factors. I just have to figure out what C3 and C4 are. So I clear the denominator, so I'm going to multiply this, and that's going to give me this equation here, which is going to give me these two equations that I can solve for C3 and C4. And you can solve these explicitly if you want. Obviously, the other thing you can do is you can, let me make this a little bigger. You can just type these into ease and let ease or Maple or whatever it is you like, let ease solve for that. So that's what I did right here. This is those two equations. That gives me C3 and C4. Okay, so at this point, I think I'm done, right? I broke this guy up into this guy. I broke this guy up into these two terms, and then this one was already fine. So if I make those substitutions, I get that. This term and this term cancel out, so I actually only get this. And this is now composed of three terms that are each easy to inverse Laplace transform. This is a constant, this is the exponential, and then this is the other exponential. Right? All right. We can plot that in ease. So that's what I did somewhere, and that's I guess obviously where I got these plots from is just substituting this into ease. And that's how you use the Laplace transform. So I think we'll stop there today. But what we're going to do next time is a couple things. One is we're going to show how you could do this entire problem once you've derived the math problem you're trying to do. How you can do the entire problem in Maple pretty easily. And then the last thing I think that we need to do, which is pretty important actually, is point out that here, getting to this point right here was actually really easy, right? And it will be pretty much equally easy even when we're doing one-dimensional problems, one-dimensional transient problems. Going from this back to the time domain has got a little tricky here. It'll get really tricky in one-dimensional transient problems. So if we could just stop right here, that would be awesome, right? And it turns out that you can. Once you get the solution in the S domain, there are prepackaged routines for doing the inverse Laplace transform numerically so that you can get back to the time domain. So we'll also show how to use those on this problem. And then next time we'll also then solve a more interesting problem that is a one-dimensional transient problem.